So, today we're going to dive into something really cool, a new kind of cryptographic shield. It's designed to protect the internet from two massive threats, one that's banging on the door right now and another that's looming just over the horizon. The whole thing is called SAPOW-KEM, and, it might just change how we think about staying safe online.
And this is a really big question, right? Because pretty much everything we do, from banking to sending a private message, it all hinges on our security protocols. But right now, those protocols are getting squeezed from two completely different directions at the same time. It's like a pincer movement. So let's break this down. We're really talking about a pair of twin threats. One is a major danger for tomorrow, but the other one, yeah, that's a huge problem we're dealing with today. Okay, so on one side, you've got the quantum threat. This is the very real fear that one day super powerful quantum computers will just shatter the encryption we use to keep everything secret. And on the other side, you've got the here and now problem, DDoS attacks. That's short for a distributed denial of service. This is where giant armies of bots just flood a server with so much junk traffic that it literally collapses and nobody can get through. So one threat is about keeping secrets, and the other is about just keeping the lights on.
So the big question is, how on earth do you defend against both of those things at once? Well, that's exactly what the research we're digging into today is all about. It's a proposal for a brand new kind of crypto shield. And this is it. The proposal is called SAPOW-KEM, and it comes from a paper by an independent researcher, Mohammed Ben Ammar Shraiti. We're going to get into a detailed summary of his really innovative work here.
This quote, right from the paper's abstract, really nails it. The idea is to build a defense that isn't just quantum-proof, but that also has a puzzle built right in to stop attackers. Now, the two phrases to really lock onto here are natively integrates and cannot be replayed. That's where the magic happens. This is the core innovation. All right, so let's pop the hood and see how this thing actually works. The secret sauce here is a really clever mashup of two ideas that have been around for a while. First up, you've got the post-quantum part. This is a key encapsulation mechanism, or KEM. And really, that's just a fancy way of saying it's built on math that we're pretty sure even a massive quantum computer couldn't crack. Just think of it like an unbreakable digital vault that's protecting a secret key. Then you have the second ingredient, proof of work, or POW. And I absolutely love this analogy. It's like a computational cover charge. To get into the club and talk to the server, your computer has to solve a tiny little math puzzle first. For the server, checking your answer is super easy. But for you, it takes a little bit of effort. Now, if you're a regular user, you won't even notice it. But if you're an attacker trying to send millions of requests a second, that tiny cost adds up really, really fast and makes the attack completely impractical. Okay, but here's the crucial point, the real game changer. Using a proof of work puzzle to protect a server? Not new. Using post-quantum crypto? Also not new. The big idea in this paper is about cryptographically binding them together into one single, indivisible process. See, the old way of doing things would be to handle these in totally separate layers. You'd have your proof of work layer acting like a bouncer at the door. And then, only if you get past the bouncer, you move on to the key exchange layer to have your private conversation. They're two completely separate steps. But this is the new way. SAPOW-KEM gets rid of those separate layers. Instead, the solution to the puzzle isn't just your ticket to get in the door anymore. It actually becomes a core ingredient used to create the encrypted key itself. What that means is that a puzzle solution is now totally unique to one specific session with one specific key, and you can never use it again. It's basically a single-use cryptographic ticket. So the whole handshake between your computer and the server now looks like this. Step 1, the server sends your computer a unique puzzle. Step 2, your computer solves it. And, this is the important part, it uses that solution to help encrypt the secret key it's sending back. And then step 3, the server gets your message. Now, before it does anything else, it does a super quick, super cheap check to see if your puzzle solution is correct. Only if it's correct does it then do the much harder, more expensive work of actually unwrapping the secret key. This design is what stops a DDoS attack dead in its tracks because it lets the server throw out all the junk requests without breaking a sweat. Now, this all sounds pretty great, doesn't it? But, with any new security idea, there are always trade-offs. There's always a cost. So what do you gain and what do you have to give up? Well, here's the biggest cost. To make all this binding work, the amount of data your computer has to send to the server goes up a lot. We're talking about an increase of around 290% compared to the standard way. And that's because you're not just sending the encrypted key anymore,
You're also sending that big 3072-byte puzzle solution along with it.
So let's look at the scorecard. What do you get for that extra data? Well, as you can see, the really important security features are all still there. You keep the highest possible level of confidentiality, cryptographers call it IND-CCA2 security, and you're still protected from quantum computers. What you add is that built-in native resilience to DDoS attacks. So the trade-off is pretty clear. You use more bandwidth to get way more stability during an attack.
And this right here might be the most important security finding in the whole paper. Adding all this DDoS protection doesn't weaken the core post-quantum encryption at all, not one bit. The security proof shows that you maintain that gold standard of confidentiality. So this extra protective layer doesn't open up any new holes. It's basically free from a security perspective.
Okay, so let's pull all this together. What does this actually mean for the future of how we make secure connections on the internet? I mean, to recap, the contributions here are pretty powerful. This is the first system to bake a lattice-based proof of work right into a post-quantum key exchange. It cryptographically locks the puzzle to the session so it can't be replayed. It bolts on DDoS protection without sacrificing any confidentiality. And it even has a smart controller that can automatically make the puzzles harder if it thinks it's under attack. And that kind of leaves us with this final question. SAPOW-KEM shows us a future where all of our devices have to do just a little bit of extra work to prove they're legitimate before they can talk. So is that extra effort? Is that the price we're going to have to pay for a stronger, more resilient internet? One that's safe from the attacks of today and the attacks of tomorrow?